This is a lecture on correlation analysis. So let's jump right in. So correlation can be one of the procedures for exploratory analysis. And the purpose is to explore the relationships between two measured variables. What is the relationship between group A and group B? Does variable A increase with variable B? Does it decrease? And so it just allows you to learn about the relationship between the two variables. So some examples, you can describe the relationship between height and weight. As height increases, usually weight increases in children who are normally developing and growing. With strong correlation, we can infer something about the second value given the first. And correlation coefficients are used to quantify the strength and the direction of the relationships we're seeing between the two variables. So here are some scatter plots that help us look at relationships between two variables. In the first graph that you see on the left, there's a perfect positive correlation. As we go up 1 unit on the x-axis, we go up 1 unit on the y-axis, and it's a direct perfect correlation. The second graph, or the middle one, is a perfect negative correlation, and just the opposite is happening. As you increase the x-axis, the y-axis goes down. And then you have the third graph where there's no correlation, and you can see they're just scattered about. And you notice across the top, the R, or the correlation coefficient, for a perfect positive correlation equals 1. For a perfect negative correlation, it equals -1. And for no correlation, it's 0. So here's some more about scatter plots. There's various degrees of linear correlation, and that, once again, that correlation coefficient helps us look at how strong positively or negatively that correlation is. So again, the first graph on your left is a pretty strong positive correlation with an R of 0.76. That's a pretty strong correlation. Now the middle graph, things are a little bit more scattered, and it's not quite as strong a positive correlation, but it's still positive. And that correlation coefficient that corresponds with that particular graph is 0.44. Then you see on the right-hand side, the last graph is a correlation of -0.69. So it's a pretty strong negative correlation. And you can see that we end up with a pretty tight cluster. As the x-axis goes up, the y-axis is going down. So scatter plots reflect the relationship between the two variables. For each score, for each participant, you have a dot. And here's an example of the absorption of a liquid medication and crushed tablets administered to a child. So you could see if there was a correlation between the two. We'd certainly expect a positive correlation. You would expect those to be similar, but that's just an example of how you could look at the relationship between those two. Now, correlation coefficients provide a quantitative measure of the relationship between the two variables. And as I said before, it ranges from a 0 to either +1 or -1. So if we have a 0 to 0.25, that's considered little or no relationship. A 0.25 to 0.5 is a fair relationship, and 0.5 to 0.75 is a moderate to good relationship. Anything above 0.75 is considered good to excellent. And we can also have the same strength of negative correlations that correspond to this. It's just you have a negative value in front of your numbers. The other thing we have to keep in mind is you can have a linear relationship between two variables, or you can have a curvilinear relationship between two variables. So coefficient R is a measure of the linear relationship, but when a curvilinear relationship exists, R won't be accurate. So you have to use the eta coefficient. And those might be things like variables such as age and strength. So as a person gets older, they get a little bit stronger. And then as they become elderly and there's a decline in strength, then it goes back down. So that's an example of a curvilinear relationship. The other example is anxiety and test performance. Traditionally, if students are a little bit anxious, they may study a little harder, they may perform a little bit better. But if they get totally stressed out, it will inhibit their ability to perform well on the exam. So those are examples of variables that we would expect maybe a curvilinear relationship. So here's a little quiz question for you. A correlation coefficient value of 0.5 to 0.75 is generally considered to indicate an association between variables that has fair relationship, moderate to good relationship, good to excellent, little or no relationship, or you can make up something of your own if you'd like. Take a few minutes and think about that question. So our answer is B, moderate to good. Remember, 0.5 to 0.75 is considered moderate to good relationship. Here's a correlation matrix, and I realize it's a little bit fuzzy, and I'm not really expecting you to read specifics in this, but it allows you to examine several variables at one time by looking at the matrix. So you're comparing multiple variables across the X and the Y axis, and it lets you look at all of them simultaneously in this matrix. And the significance on a correlation coefficient does not indicate the strength of the relationship, just that the difference is unlikely to be the result of chance. So you have the strength, which we've already talked about, and then you also have an indication of significance, if it's thought to be as a result of chance or not. So curvilinear relationships are best tested with the R statistic. True or false? The answer is false. Remember, we said it was the eta statistic. So now let's talk about the Pearson product moment correlation coefficient. It's the R for sample data and the rho for population data. And it only can be used when X and Y are continuous variables and there's normal distribution of those variables, and it has to be interval or ratio level data. You can use the Spearman rank correlation coefficient, which is abbreviated as R subscript S, and that stands for the Spearman rho. And it's the non-parametric analog to Pearson's R, and it can be used with ordinal data. The phi coefficient, which is abbreviated, as you can see there with the circle and the line through it, is used when both X and Y are dichotomous variables. So it's a special case of the product moment correlation coefficient. But some examples are if you have pass-fail for a group of N class exams for baccalaureate and associate degree nurses. So you have two dichotomous variables, pass, fail, and baccalaureate or associate. Another example is breastfed at discharge and 3 days later. So those are yes, no variables. Now, when you have both dichotomous variables and continuous variables, you can use the point biserial correlation. So again, it's the R with a subscript PB. And it's used when you have one dichotomous variable correlated with one continuous variable. And it is also a special case of the product moment coefficient. It's calculated using the Pearson correlation, and the degree to which the continuous variable can be used to discriminate between the two categories of the dichotomous variable is the finding that you get with this analysis. So your next quiz question. The phi coefficient is used for A, when X and Y are dichotomous, B, when the X is a continuous variable and Y is a dichotomous variable, when the X is dichotomous and Y is a continuous variable, none of the above. So remember, phi coefficient is used when X and Y are both dichotomous. So let's talk just a little bit more now about correlation versus comparison. Correlation's based upon covariance, not upon differences between means. So the correlation's based upon whether there's covariance with the variables. If a change in X is proportional to a change in the Y score, covariance is high. Causal relationships are best established under controlled experimental design. If that's not possible, sometimes we use correlation, but it must meet certain criteria. There need to be biological credibility of the association. There needs to be a logical time sequence. The cause has to precede the outcome. A dose-response relationship should be evident. A larger cause equals a larger outcome. And there needs to be consistency across several studies. And that sort of summarizes what I was going to tell you about the correlation analysis.